Let's learn how to factor trinomials when the leading coefficient is equal to 1. In a previous video, I discussed the difference between the two cases of trinomials. It's important to recognize these two cases as it affects our factoring strategy. This video is centered around how to factor trinomials when a equals 1. This is a slightly easier case. Let's say we have a trinomial in standard form, so it's unfactored. Let's assume a equals 1. If a equals 1, we do not need to write it. Our trinomial will have this form where the coefficient of x squared is 1, the coefficient of the middle term could be any number, and the constant term could be any number. The variable could be x or it could be something else. That doesn't change too much. To factor this case, you can draw two sets of parentheses. In each of those parentheses, we're going to put a binomial. Remember, a binomial means a two-term polynomial. Because a equals 1, the first term of each binomial will simply be x, or whatever variable you may have. Remember, the first must multiply together to give us the first term, which is x squared. Now we have to find two numbers that add to equal the middle coefficient and multiply to equal the last term. The reason this must be true is due to the distributive property, or you can think of it as foiling. I go into this in more detail in my previous video. So for trinomials with a equals 1, this is the strategy we use. We draw two sets of parentheses with x as the first term for each, and then we have to find two numbers that satisfy these conditions. Let's look at an example. We're asked to factor this polynomial. How many terms does it have? 3. That makes it a trinomial. That means we need to determine which case are we in. The coefficient of x squared is 1, thus we're in the case when a equals 1. Therefore, we can employ this strategy. However, before we get started with that, we should always check for a GCF first. Remember the factoring flowchart? Before we start anything over here, we have to start here. In this case, the GCF equals 1. Notice the GCF will always be 1 if you have a standard trinomial with the leading term x squared and leading coefficient of 1. Since the GCF is 1, we cannot factor it out, and we can proceed with our trinomial factoring strategy. Remember, our strategy, because a equals 1, is to draw two sets of binomials. The leading term for each set will be x, since our variable is x. And we simply need to find two numbers that add to equal the middle 13 and multiply to equal the last 30. The way we do this, because there's so many options that could add to 13, don't start with that. Instead, start with thinking of the factors of 30. When we talk about factors of a number, those are two integers that multiply to equal that starting number. So if we find factors of 30, that means two integers that multiply to equal 30. So the pairs of numbers that we put in this column will be candidates, possible values for the two numbers that we're looking for. The first pair of numbers that we could think of is 1 and 30. If you multiply those two together, 1 times 30, you get 30. Therefore, 1 and 30 are factors of 30. Notice that 1 in the number will always give you a factor pair of that number. Is this the factor pair we need? Well, the two numbers must satisfy both of these conditions. Anything in this column should be factors of 30, so that will automatically satisfy the second condition. However, we need to check if they satisfy the first condition. To check that, I'll make a second column with these two numbers added together. 1 plus 30 produces 31. Do the two numbers add to equal the middle? No. The middle is 13. The two factors added to 31. This tells us these two factors are not the numbers we're looking for. We have to try a different pair of factors. If a number is even, then you know 2 is a factor. So the easiest way to get the next factor pair is divide 30 by 2, which gives us 15. Therefore, 2 times 15 equals 30, so we know 2 and 15 are another factor pair. Because 2 times 15 equals 30, we know that 2 and 15 satisfy the last condition. But do they satisfy the first condition, that they add up to the middle, which is 13? Well, let's check. 2 plus 15 equals 17. This is not the middle, which is 13. Therefore, 2 and 15 are not the numbers we're looking for. We proceed like this, looking for factors, until we find a pair that adds to 13. Let's think of another factor pair. Is 3 a factor of 30? Yes. 30 divided by 3 equals 10. Thus we have another factor pair. Now let's check the next condition. Does 3 plus 10 equal 13? Yes. 3 and 10 are two numbers that add to equal 13 and multiply to equal 30. Thus, 3 and 10 satisfy both conditions. 3 and 10 are the numbers that we were looking for. Putting those numbers into their spots gives us the factorization. This is our answer. It's always a good idea to check your factorization. You can do this by multiplying, which gives us this, which is the same as the unfactored form of our polynomial. This confirms that our factorization is correct. Let's look at another example. We're asked to factor a polynomial. How many terms are there? 3. Thus, this is a trinomial. What's the leading coefficient? 1. Thus, we're in this case, and we know what strategy to use. Before we start our strategy, though, we must check for GCF. The GCF in this case is 1. Thus, we do not need to factor anything out, and we can proceed with our trinomial strategy. We must find two numbers such that they add to equal -11 and multiply to equal 24. We draw our two sets of binomials and get started with finding these two numbers. 1 and the number itself are always a pair of factors. So we know that 1 and 24 will satisfy the second condition, but will it satisfy the first? 1 plus 24 equals 25, which does not satisfy the first condition. Thus, we reject this factor pair. We keep going until we find a factor pair that satisfies both conditions. Let's notice something about the first factor pair. positive 1 plus positive 24 gives us positive 25 when we add them. And 1 times 24 gives us positive 24. However, there's a second option. We could do negative 1 and negative 24, as those would also multiply to equal positive 24. So we see that for every factor pair, we have a positive option and a negative option. But we want to limit our choices to make the process faster. Noticing that the middle term is negative, we conclude that the factors cannot be positive, as two positive numbers added together will never be negative. As we proceed, we can only consider the negative options, and this will keep our option list shorter. Unfortunately, negative 1 and negative 24 still won't work, as those added together gives us negative 25. The next factor pair is negative 2 and negative 12. Adding those together gives negative 14, which does not work. The next factor pair is negative 3 and negative 8. Adding those together gives negative 11, which works. Thus, negative 3 and negative 8 are the two numbers we need. Putting those into their spots gives us the factorization. We can simplify this, though. Plus and minus is simply minus. Thus, we have our answer. Please note that multiplication is commutative, so we could change the order, and the answer would still be the same and still correct. As always, we should check our answer by multiplying, which gives us this. Now, does this equal the original unfactored polynomial? Yes. Therefore, our factorization is correct. If it did not equal the original polynomial, our factorization would be wrong. In the last example, we did a sign analysis to make the number of factors we had to consider shorter. Here's a summary of that factor analysis. If the sign of the last term is positive, the sign of the sign of the middle term is positive, the sign of the two integers you're looking for both have to be positive. If the sign of the last term is positive, but the sign of the middle term is negative, the sign of either the two integers you're looking for have to both be negative. If the sign of the last term is negative, then one of your integers will be positive and one of your integers will be negative. If the sign of the middle term is positive, the larger of your two integers will be positive. If the sign of the middle term is negative, the larger of your two integers will be negative. You can use the sign analysis to make your list of possible factors shorter, thus making the factorization easier. Let's do one more example. This polynomial has 3 terms, and we're asked to factor it. Thus, it's a trinomial. However, notice that the leading coefficient is not 1. So as it stands, we cannot use the factoring strategy we did in the last 2 examples. However, before we keep going, we have to remember to check for the GCF. In this case, the GCF is 3. Thus, we can factor out the GCF, which results in this polynomial. Now, this polynomial is in factored form because it's the result of 3 multiplied by this trinomial. However, we always want to completely factor. We now can look at the resulting trinomial inside the parentheses and consider if we can further factor that. That's a trinomial with a equals 1. So the strategy we've learned will apply to that polynomial inside the parentheses. Whenever you start a factoring problem, think through this flowchart. The first step is to factor out the GCF. We just did that. Then look at what's left. How many terms does it have? In our example, it had 3 terms, so we need to proceed with the trinomial factoring. Then, with trinomial factoring, we have to decide which strategy to use depending on the case. For our example, we're in this case. Let's focus on just the inside trinomial for a second, factor that. But then for our final answer, we'll have to make sure we include the 3 that we factored out in the beginning. To factor, we set up our two binomials. However, notice that the variable is m this time. Make sure that whatever you put here multiplies to equal the first. If I put x's, that would not work, because we need to get m squared, not x squared. Now we must find two numbers that satisfy these conditions. Before we start looking for the numbers, let's do our sign analysis. B is negative and C is negative, which tells us we need one of the numbers, the larger one, to be negative and the smaller one to be positive. Keeping this in mind will help us limit our list of potential factors. Let's look for factors of negative 20. The option is 1 and negative 20. Now, again, I could have done negative 1 and positive 20 because that also would multiply to equal negative 20. However, based on the sign analysis we just discussed, I know the larger number must be negative in order to add the two numbers together to produce a negative. Thus, I can limit my list of possible options. Unfortunately, this factors will not work because 1 plus negative 20 equals negative 19, not negative 8. Let's think of a next set of factors. We can do 2 and negative 10. Again, I made the larger number negative, the smaller positive. Add those two together gives us negative 8, the number we need. Thus, 2 and negative 10 are the numbers that satisfy the two conditions. I want to point out there are more factors of negative 20. However, they would not satisfy the second condition. There's only one set of numbers that will satisfy both conditions. That is, factorizations are unique. Once you've found the pair of numbers that work, you can stop. We place these numbers into their spots, and we have the factorization. We can simplify this a little bit though. So this is the factorization of this polynomial. However, that's not the polynomial we were asked to factor. We were asked to factor the original polynomial. We had to go on a little side journey to factor this inside part. So now we can replace this inside part with its factored form to arrive at the final factorization of the original polynomial. So don't forget to include that 3, the GCF, that we factored out in the beginning. If you just put this as your answer, that would be wrong because that does not equal the original polynomial. We have to include the 3 in order for this to equal the original. As always, we should check our answer by multiplying. To multiply, first we can FOIL the two binomials, giving us this. Next, we can distribute the 3, giving us this. Does that equal the original polynomial? Yes. Therefore, our factorization is correct. We learned how to factor trinomials with the leading coefficient of 1.